Let's look at the basic elements, the single elements, single and multi-port devices. And so in here we'll come back and say, okay, look, if you have a system in different energy domains, like in this case, in the mechanical system, you have a mass that a force has been applied and the mass is a consequence of this moves. In an electrical system here, you have that you have this voltage and this resistor. Always this interaction between the battery, let's say in here, voltage source and the resistor generates a current, yeah. So you have two variables that control this kind of example, the force and the velocity. This one is the voltage and the current. This is a rotational flywheel where we apply a torque. And then the variables are torque and omega. And this one right here is pressure times volume flow rate. Okay. What I want to say about this is that you notice in all these examples, it has two variables that if we look at them a little closer, they do similar things, but because they are in four different energy domains, then we have to use the variables for that. But however, the idea that Professor Painter had when he invented bond graphs was precisely this, that the elements interact with each other with certain way and with the variables that are common to them. For example, F is the force, it's like the current on like the voltage on an electrical system. Or it is the inflow, or is T. T is for torque, and in here you have power is P and P times Q. In all these examples, the variables, although they have different names, they do the same thing. Except like a capacitor on an electrical system. Nowadays, could be a capacitor on a mechanical system if you consider a spring, for example. But in this case, on the examples that you have in front of you, the point is that there's two variables that always produce power. Okay, so what Painter is saying is that we can use, because they all interact with power, that we should be able to create a common notation for getting these things done. And in here you have newtons and volts and meters, and pressure is Newton per meter squared, and on the other side the flows, velocity, current, angular velocity. I think the idea was that Professor Painter says there's two families of variables. One family of variables, we are going to call it therefore variables. The other family, we're going to call it flow variables. But always the product of one effort variable and a flow variable in that domain will produce power. That's why on a mechanical system you have force and velocity. On this one in uh, the electrical system, voltage and current. Or if it is in rotation, you have a torque and the angular velocity, or you have the pressure and the volume flow rate. All these are variables of the same kind. So you could say that if you examine it downwards, you could say that this force behaves like a voltage, behaves like a torque, like a pressure within this family. But each one, while they might be alike, they're not the same, and the units are different. Okay, so here the flow. Okay, so effort times flow, always power. It's much easier to remember two variables than remember 8 variables, like the ones we have in here. Now, we have to realize that there are relationships between the variables that we are just proposing. We have this tetrahedron of a state. Some people call it painter's tetrahedron of a state. But in here, the relationship between the effort and the momentum is through this derivative dp dt, and the relationship between the flow and q is also between. So that's how we make the q the independent variable, and the other one, in the other case, we make the p also the other variable. So in this is the tetrahedron of a state that relates the effort and the flow, as well as the momentum, the position and the momentum, because that's what it is. In here, this is the force and angular velocity, and this is going to be the position and the momentum. But in, yeah, so this is the tetrahedron of state. Now, instead of, see how many variables we have, 1, 2, 3, 4, times 4, there are 16 now. And I don't think that it's easier to deal with 16 variables as opposed to dealing with 2 in the in here on the left hand side, the effort and the flow and the displacement and the momentum are the variables that we use. So instead of 16 variables, we have reduced it to 4. So when we talk about an effort, we might be talking about a voltage, a pressure, or a force. When we talk about a flow, we might be talking about the velocity, the angular velocity, or the current or the volume flow rate. Now this displacement is another generalized variable that relates to the flow, and then you have the displacement, the momentum. So 4 variables one effort and a flow, and then you have this displacement which is normally q, and momentum which is normally p. So those are the variables we'll be using. This is an interesting concept in here because I am telling you that bone graft models are like also like junction models or connection models. Um, in your textbook, you see this examples like this that are word models. I mean, much easier than that you can't get. You have the battery on one side, and then you have the motor on this one over here. And then you have the Bendix is the little gear that cranks the engine. But between this, see, there's the chemical domain, you may say, some chemicals in the battery transform into voltage and current, and the current transform into a torque and angular velocity. So that's the idea behind creating models, is to see how the elements are connected with each other. And once we do that, we will be able to do simulations. Now this is a more complex word bone graph than the one that we just saw. In this case, you see on the left hand side, you have the engine here, and then you have the clutch, and then we have the gearbox, we have the drive shaft, and then we have each of the wheels. Of course, between this we can add a bunch of other elements, but the point is that this is a realistic model of how a model of vehicle performance could actually be built. Okay, the layout, looks like the rear car, with the drive shaft being perpendicular to the rear axle. And in between those two, there is this differential gearbox. Okay, any question about this? Okay, let me do this. We need to establish what the elements, what kind of elements do we count on to do these simulations? How can we get the connections done correctly? It has been discovered that with 9 elements, you should be able to do everything. So you have these basic elements where there are two sources. You have in this case, you have the effort junction, and you have a zero junction, a 0 and a 1. Those are the tools that are used for creating the connections between elements. And in here you see you have the inertia element, capacitive element, resistive element. You have the transformation, and then you have the gyrator. So using these elements, and again generalized elements, you can do models across the disciplines, because with the same symbol I in here, I could be representing a mass or an inertance on an electrical system, or um, some in here you have the I, the C, and the R in a mechanical system or electrical system. They have the same symbol. They do different things and do different units, but they belong to the same family. So a C in a mechanical system like spring can be compared with a capacitor in an electrical system. Okay, any questions about this? Okay, let's go over here to this concept of power flow and the causality. I already outlined this causality in a little while ago when I show you that slide of the equivalency. Yeah, but in this case you can have that if you only draw this half arrow in there, indicates the way power flows. It goes from A to B or goes from B to A. When you have this causal mark, then it's not ambiguous at all. It is exactly what needs to be to indicate that if you were to hold it like here, it's like A pushes on B, which is obvious. I think this one is like B pushes on A. So you have two little things to complete on each one of these connections. I told you that these bond graphs, they help the connections between elements. Like on the first example here, this one here, A is like transmits the power to B. This one is the other way around. But the causal concept establishes a relationship for this form in terms of this, or a relationship like this. So it could go either way. Any question about this? No? Now, the elements that I showed you are individual elements like ICs and Rs. But there's two of those elements that are used to indicate how things are connected, and which variables add and which variables subtract and which variables stay constant. In the case of a mechanical system, such as the one I have on the left-hand side over here, the velocity is common to all the elements. Do you see that? If I move this is going to follow, and so this one. So, but if I have it connected this way, I use it like this. It all depends on how we have the connections done. So you can have the connections like this. So this will be an I element, C on the R. Or you can have it in here, great. Any questions about this? Do you notice the connection in here? This one it connects with the common flow variable, and this one connects with the common effort variables. In this case, the displacement is the same in all three. In this case, no, we have to add. Okay, so that's um, the discussion about the different elements. I say the different elements, variables, and these two connectors that we need. We need this. We need a zero connection and a one connection. I think we'll study a little later in detail more about those, but for now, please understand that either we use a one and a zero depending on what we need to do, which variables need to add or which variables need to be constant. Okay, this is the introduction to these elements. Any questions about this? Hmm? I see some of you are printing them out, and as I talk on these notes, feel free to write them in there, or you can do it electronically also. Let me show you how to do it in case you are want to make annotations on what I'm doing.